This here is a classic energy problem. The spring is a dead giveaway, but as you read it, it says this bar, I think it says the right end of the bar drops, oh no, it says it rotates 36.9 degrees clockwise. What's the angular velocity after it rotates? So you have a starting position, and there's weights dropping, there's springs stretching. This is definitely energy problem. So the first thing I did was 36.9 degrees. That sounded familiar. I took the tangent of that and was 0.75. That means it's a 3, 4, 5 triangle. So that'll be handy to know later. Okay, so energy problem, again, you track the four things: 1/2 mv squared, 1/2 I omega squared, mgh, and 1/2 kx squared. When you do the mgh, you need to pick a datum, and whenever you have something horizontal, it's kind of a good idea to just take the datum right there along that horizontal. Okay, and you're going to track where the center of gravity moves relative to that datum. Okay, this is a unique problem, and I think it's the first time. We've always had start from rest, but this problem says it's going at 2 radians per second when it starts, so it has an initial velocity. So the initial 1/2 mv squared is 1/2 m, and the velocity. So again, that little trick, you look for the little pins. There's a pin there at A for sure. So B is definitely spinning around A. The distance from A to the center of gravity is 3 feet, 2 radians per second, so the velocity is 2 times 3 and squared, 1/2 mv squared, 1/2 I omega squared. You're going to have to know the mass. Don't forget, if it's in pounds, you divide by G, so the mass is 2 slugs. And this is a slender rod, so it's 1/12 mass times length squared. That's the radius of gyration, the moment of inertia. Okay, I'll let you plug those numbers in. Okay, so then mgh relative to the datum. So before we pick the datum, so we'll go right through the horizontal rod, so it's 0. And so 1/2 kx squared. The spring at this instant is 4 feet long. And so we're going to have to read the problem carefully to look for the clues, what the unstretched length was. Well, this time they just tell you, oh, the unstretched length is 2.5 feet. It's 4 feet right now, so that means that it stretched 4 minus 2.5. And so it's going to be 1/2 k delta x squared. Okay, so afterwards, when it's at this 36.9 degrees, the length is 6, and because it's a 3, 4, 5 triangle, I figured out that it was dropping 3.6 feet. So if the right end drops 3.6 feet, the center of gravity drops 1.8 feet. It's halfway over. Okay, so after, you have 1/2 m. The velocity is going to be this unknown omega afterwards times 3 squared, 1/2 I omega squared, and it has an mgh of the weight, 64.4, times the height, 1.8. We figured out by similar triangles, and it's going down, so it's negative. And then lastly, there's the 1/2 k delta x squared. If you look at the picture, the spring is now 7.6 feet. Unstretched length is 2.5. 7.6 minus 2.5, or 5.1, is how much it stretches, and that'll be squared. There's only one unknown in here. You add up everything before equals add up everything after, and the only unknown is omega 2, and you can solve for that.